Welcome back to our last section on circuits. We're going to start out discussing some safety devices. First, we have a fuse, which is a short piece of metal that melts when too large of a current passes through it. Next is a circuit breaker, which is an automatic switch that opens when the current reaches some set value. Now, these two probably are familiar to you if you've ever looked in your house, especially like in a closet. There's a panel on the wall that has different switches in it, and that's where you can find your circuit breaker. So if you've ever been in a room and you have too many things going on at once, like maybe you're in the kitchen, you have the oven and the microwave and the dishwasher, and then it blows a circuit, you have to go back to that panel, and then you can just put the switch back over, and that'll reset everything. And what this does is it helps turn the current off if there's going to be too much, so that it doesn't create a fire. Next, we have what's called a ground fault interrupter, and this device detects small differences in current, and it'll prevent dangerous shocks in case you have too much of a fluctuation. And then lastly, if you ever hear the term short circuit, this is something that occurs when a circuit is formed that has a very low resistance, and then just a reminder that a low resistance would cause a large current. And for all of these safety devices, we're trying not to have too much current go through, because what that does is it'll cause something to heat up and it could potentially start a fire. So far we've had series circuits and parallel circuits. Now we're going to combine them together. So you can Google reducing circuit diagrams, and that'll give you some problem-solving strategy. And then I also included some steps here for you as well. We'll be going through each of these when we do our example problems. It's always helpful to draw a schematic diagram, and then we're going to find the equivalent resistance for any parallel resistors, and then we can redraw a new schematic diagram for that new equivalent, and then we're going to reduce that circuit down and find the equivalent resistance for any series resistors and draw a new schematic for that, and then we can keep reducing that down and apply Ohm's law as needed. So for our first example problem, you're given a combination of series and parallel together, and you're asked to find the equivalent resistance. So even though you do have the voltage for the battery in the circuit, we don't necessarily need it because we're only interested in the resistance. So the first thing we want to do is take what resistors are in parallel with each other and find that equivalent. So let's do that first. Remember, for parallel circuits, you want to add the inverses, and this will give us a decimal value of approximately 0.046 repeating. And then we will take the inverse of that answer, and we come up with an equivalent resistance of about 21.4 ohms. So now what we're going to do is redraw the schematic diagram with this value in place of where our parallel resistors were. So what we've done is, instead of drawing these two resistors in parallel, I've replaced them with one resistor that was the equivalent resistance that we found. Now this looks like a series circuit, and we can find the equivalent resistance for this new circuit by simply adding our two resistors together. And this gives us a new equivalent of 23.4 ohms. And this would reduce both of those resistors down to 1, so that makes this our final answer. For our next example problem, we have a combination of a 12 and 4 ohm resistor in parallel with each other, and then those are in series with these other two 3 ohm resistors. So first, we want to reduce the parallel resistors down to 1, so let's do that. So we're going to add the inverses together and come up with 0.3 repeating, and then we take the inverse of that to get our actual equivalent of 3 ohms. And then if we were to redraw the schematic, it would look like this. So I've replaced that parallel section with the equivalent resistance that we found, and notice that the equivalent resistance between points A and B splits up into two current paths. So what that's going to do is make these two in series with each other, and then that equivalent will be in parallel with this one. So let's reduce this section down. For a series circuit, the equivalent resistance would be simply adding those two together. So we've got 6 ohms And we can redraw the circuit again. So I've replaced these two in series with each other and reduced them down to one resistor and redrew my schematic. Now we can see that these two are in parallel with each other. So we need to find the equivalent resistance by adding them in parallel. So I'm going to add those inverses. And I end up with 0.5, and then I want to take the inverse of that to get my equivalent resistance and have a final answer of 2 ohms. So on your test, you'll be given a circuit that's a combination of series and parallel together, and then you'll be asked to reduce all of those resistors down to one equivalent resistance. For our next example problem, we have a practical application. This is something you might actually see. We've got a hairdryer with the resistance of 12 ohms and a lamp with the resistance of 125 ohms are in parallel with each other to a 125 volt source. And then that parallel part to the circuit is connected in series with a 1.5 ohm resistor. So we're asked to find the current that goes through the lamp when the hairdryer is off and when it's on. So first we want to list everything that's given and also draw a schematic. So take a moment and do that, please. And remember the A, B, and C subscripts are pretty arbitrary. I just happen to label the 125 ohms as A, the 12 ohms as B, and resistor C up here is the 1.5 ohm. But you do want to make sure that your hairdryer and your lamp are in parallel with each other, and then those two are in series with the 1.5 ohm resistor. And then my voltage source is drawn over here. So first, we're asked to find the current through the lamp when the hairdryer is off. So what I did was consider the circuit and the schematic diagram and turn the hairdryer off, which means this entire section, that parallel branch, would not be needed. And what that does is it allows my equivalent resistance to be these two resistors in series with each other. And that's what I've indicated right here. So first, I would find that equivalent resistance of those two right here in series with each other. So I'm simply going to add 125 ohms plus 1.5 ohms. And that's going to give me 126.5 ohms as my equivalent. And now I can apply Ohm's law and find my circuit to be the voltage of the source, which was given originally in the problem as 125 volts. And then I'm going to divide by the equivalent resistance that we found by adding those two together in series. And we see that our current is slightly less than 1, so we're going to have 0.99 amps of current. So this is when the hairdryer is off. In part B, now we're going to turn that on, so we'll have a series parallel combination. So now we have our original schematic diagram, and the first thing we want to do is find the equivalent resistance of the entire circuit. So we're going to follow the steps that we did earlier, and the parallel equivalent is going to be first. So I'm going to say 1 over 125 plus 1 over 12. And we end up with this fraction. Don't forget to take the inverse. What this does is this is the equivalent for just the parallel part to the circuit. So if I were to redraw that schematic diagram, it would look like this. So I keep my original 1.5 ohm resistor, and then I replaced the parallel equivalent with what we found right here. Now we want to reduce those two resistors. They are in series with each other, and find an equivalent with this new circuit. So I'm going to take resistor C, which was 1.5 ohms, and add to that the parallel equivalent, which was 10.9. And we see we have a new equivalent resistance of 12.4 ohms. Now we can use Ohm's law to get that current. So we're going to find the voltage from the source over that final equivalent resistance. So I'm going to take my 125 volts, because that didn't change, and now plug it in with that total new equivalent resistance. and you should discover that we end up with a current of about 10.1 amps. And notice that's a lot bigger than the 1 amps previously when the hairdryer was turned off. So hopefully you can tell that when you add resistors in parallel with each other, that decreases the overall resistance, and what that does is it increases the current dramatically. So if you have a lot of appliances going on at different times, then they're wired in parallel with each other, and if you turn on too many of them at a time, that's going to make your current increase, and that's why we need those safety devices so that you don't start a fire with too much current running through the wires. And lastly, we're going to look at our ammeters and voltmeters. You should have had practice with these in your labs. I just wanted to double check and make sure that you know what each of these devices do and how they should be connected in your circuit. So remember that an ammeter is an A with a circle around it. Its purpose is to measure the current in any branch or part of a circuit. And an ammeter should have a low resistance so that it doesn't actually change the current that's going through the circuit you wish to measure. And it should be connected in series. And lastly, we have our voltmeter, which is a V with a circle, and it's used to measure the voltage drop or electric potential difference across some part of a circuit. A voltmeter should have a very high resistance, and the reason for that is because it's going to be connected in parallel, so we want it to cause the smallest possible change to the current that you're trying to measure. That's it for our circuits chapter. Good luck on your test.